Hey everybody, so in this video I'm going to be showing you an example of an application of the instantaneous center of zero velocity by doing this problem right here. So to begin with, the way it works, it goes back to the equation that says like VA is equal to VB plus the cross product of omega with the position vector going from B to A. Okay, from B to A. So what this means is that we have a body. So in this case, the body is this rod right here. Okay. So it says that we have two velocities on this body. Okay. In this case, we have velocity VA, and then we're eventually gonna have VB because as the rod slides down on this end, okay, it's gonna have to compensate on this side by moving to the right, because then it's gonna look something like that, and then something like this, and then eventually completely flat on the ground. So we're going to have velocity VB right here. So back to the equation. We have two velocities applied on this body, and so this body is what connects the two velocities on the opposite ends. Okay, so, and the reason why I said this is because this applies to the instantaneous center of zero velocity. And first we want to locate where the IC point is. Okay, I'm going to abbreviate instantaneous center of zero velocity as IC. Okay, the IC. So where the velocity is, okay, at each velocity you're going to draw a perpendicular line. So this is the velocity right here going downwards. We draw a perpendicular line like that. And then the other velocity, VB, right here has to be in this direction. Okay, it's not going to go up at an angle. Or we know for sure that it's going to be at horizontally to the right. So we draw a perpendicular line. Okay, and where those two lines connect, that's where the IC point is going to be. So, okay, it happens to be not on the body that's rotating, and that's fine. So the formula now that we could easily find the angular velocity of this body, okay, as it moves down on this end and moves to the right, we know it's going to be rotating counterclockwise just by visualizing its movement, because once this drops, okay, this would then be here, and then that's going to move there, and you see it rotating like that. Okay, so now we could just choose any of the two velocities and find a position vector going from the IC right here to either of those two. So we're just going to pick VA, and it could work if we picked VB. It'll work just the same way. So VA is equal to omega of that body that it's part of, okay, just times the position vector going from IC to A. And that would be, and we're solving for the omega, so we divide on both sides. But what is this R vector? This R vector goes from the IC to VA, and that would just be a vector, like a horizontal vector with a distance of 3, as we see right here. So that would be VA, and let's say VA was given. Okay, usually it is given, you need something to work with. So VA, let's say, is equal to 6 meters per second. So that would just be 6 is equal to omega times 3. And then you divide by 3 on both sides, you get omega equal 2.